Hello everyone, welcome to Code Black's YouTube channel. In this video, we're going to look onto a very important topic under microcontroller programming, which is ADC. Since we live in an analog world, we need to convert the analog world data or signals into digital world signals. So that digital world signals can be processed and can be used to obtain data. In this process, the ADC plays a major role to convert those analog signals into digital, such as all the microcontrollers has a function to convert analog data to digital. The AVR microcontrollers too has that function. In this video, we will be clearly looking on how to program a ADC converter, how to use it, and how the functions are be done. So let's jump onto our video. ADC, analog to digital converter. The name itself depicts what it is. This is the most widely used device in the embedded system. As I mentioned you before, since we live in the analog world, we need to capture and gather data as an analog signals and convert it to digital signals, which can be used, read and stored as digital signals in microcontrollers as well as in other programming structures. For this, we need something to convert one signal type to another, so there comes ADC to help us. When we take AVR Atmega series, normally it has a 10-bit ADC inbuilt in the controller with 8 channels, so you can connect directly 8 different analog devices in order to gather data. And also this will help to convert the data which it gathered using those sensors or devices, and it will use it to process and execute the commands which you have programmed it. Let's look further on how this works. First of all, let's look on to the ADC pins in Atmega32. The port A is dedicated for ADC input channels. It means from the pin number 33 to pin number 40, those 8 pins are the ADC channels of an Atmega16 or 32 chip. And also we have a ADC reference pin, ADC ground pin and ADC VCC pin, which is used to power, ground and provide a reference voltage, and we will look on what is a reference voltage further in this video. And remember, these 8 channels are where you need to connect your analog devices in order to convert the data and use it. As I said before, it is a 10-bit ADC which is available in Atmega chip. So simply that means 2 to the power 10, which is 1024. So finally we will be able to get an output in the range which varies from 0 to 1023. So whatever the data which you provide, it can be divided into 1024 steps and get more accurate values. So when the value is more smaller, the accuracy is high. For example, when you give with a step size of voltage reference which is 5 voltage, so it will be divided into 1023 parts, which will be like 4.88 millivolt. So you will get the data with the accuracy of 4.88 milliwatt. So you will be able to look for changes for like 4.88 milliwatt. If you want more accurate readings or more sensible readings, you can change the voltage reference. And also ADC gives 10-bit output. For that we use two separate registers, which is ADCH and ADCL. Those are 8-bit registers, so altogether we have 16 bits. As per our requirement, we can use like two set of 10 register bits and store our data. We have two options, such as to use the upper bits or lower bits to store the data. And also, as I mentioned before, we have three options for voltage reference. We can directly use the AVCC, which is used to power up the analog digital converter, or else the internal voltage, which is 2.6 volt, or else we can connect an external voltage reference pin to RF, which will be used in our ADC conversions. The total conversion time is dependent on the crystal frequency, and also we will be using ADCS0 and ADCS2 to divide the frequency and to get the adequate frequency which will work with ADC in Atmega or AVR microcontrollers. Now let's look on to ADC registers. In AVR ADC, we need to understand the main registers. There are main 4 registers which we use to do the conversion from analog to digital and save it. For this we use basically ADCH and ADCLs, which I earlier mentioned, to store the data. Both of the registers has each 8 bits, so altogether we get 16 bit, and as per preference we can use the 10 bits of it and store our data. Next we have ADMUX register, which is a very important register, and also this will help you to select the channel to be read on that particular moment. So this is also a very important register in ADC conversion. And the fourth one, and also the last but not the least very important one, ADCSRA. ADCSRA is the register which controls the state of ADC conversion, to initialize, to convert, to store, and to refresh the state. When we take the ADMUX register, we have 8 bits in which the last 5 bits are used to select the channel, and the others are used to select the reference and adjust the results storage method. So we use the bit number 7 and 6 to select our reference voltage. As I said before, we can use it by setting 00. We'll use the ADC reference voltage, which we have to give and plug into the microcontroller externally. As well as when we set it to 01, it uses the AVCC, which is used to power up the analog digital converter in the Atmega or AVR microcontrollers, or else we can use 10 or 11 as per our need to have more accurate readings and to accompany our process. And also the ADLAR register is used to set whether the data is stored in the left justified manner or else data is stored in right justified manner. As you all can see, we have like in the left justified manner, it will solely use ADCH 8 pins and 2 pins of ADCL, and also when it is right justified, it solely use the ADCL and 2 bits of ADCH. So it is also up to you to choose whether it need to be left justified or right justified and to store the data. And the rest is the AD mux bits. So bit 4 to bit 0, those 5 are the AD mux selection bits, which is used to select the channel which is needed to be read at that moment. Selecting channel is very easy, just put the channel number in the mux registers. So if you need to read the data from the channel 1, you can directly put 0001, which is given here, or else you can select some other pins which is needed to be read. Like if it is 5, you have to convert it to decimal value, the decimal number into binary values, which gives you 101, and since it is a 5-bit, 00101 will give you the number 5, so it will start reading the channel number 5. So it is simple as that to select the channel gain selection bit using AD mux bits. So these are the basic things about the initial 4 register, which is used to initialize the setup. Okay, so another very important register when it comes to ADC is ADCSRA Register. Finally, this is used to control and regulate the actions which is done through ADC. In this it has 8 bits as usual, and also each bits are used to do and regulate or start something related to ADC. The bit 7, which is known as ADEM or ADC enable bit, by writing 1 to this bit, we start the ADC, or we just turn on the ADC, as well as writing 0 to this will turn off ADC. And also the ADSC, the start conversion bit of ADC, is used to start the conversion. Writing 1 will start the conversion of ADC. And the bit 5, which is ADATE, which is the auto trigger enable of ADC, writing 1 to this bit results in auto triggering of the ADC is enabled. So simply by writing on to these 3 bits will enable their functions, and writing 0 will stop their function. So using these 3 bits, we can start the conversion, we can enable the ADC, and we can enable the auto trigger mode in the ADC as well. The next one is the ADIF bit number 4, which is the ADC interrupt flag. This is set 1 when the ADC conversions are complete and data registers, which is used to store the data, are updated. So this will basically give the idea whether the process is done or not. And also the interrupt enable the bit 3, which is used to start or trigger an interrupt once the ADC conversion is completed. And also ADPS, which is the prescaler bits of ADC function. The ADC Prescaler function is basically used to regulate the frequency or the crystal frequency of the microcontroller as per the ADC requirements. By this, we can determine the frequency of external frequency to use in the conversions. In AVR, ADC demands an input clock frequency should be less than 200 kilohertz. So whatever the external So whatever the external clock frequency you use, make sure that you use the proper division factor, which gives you a value which is less than 200 kilohertz. So most commonly the clock frequency which is used will be around like 8 megahertz or 16 megahertz. If we take an 8 megahertz clock, if we use 64, we will get something around 125 kilohertz, which is less than 200 kilohertz, which is a good sign to use. But we can't use the 32 divisor because it will give something around 250 kilohertz, which is higher than the adequate frequency. So it depends on the external clock frequency which you use, and also the conversion rates which you need to be done. So make sure every prescaler bit is selected in order to keep the external frequency, which should be below 200 kilohertz. Now it's time for like start recording and test the ADC function, whether how it works or what sort of a thing which we can get out of it by using Proteus and Microchip Studio, which is the new updated version of ATMEL Studio. As we move on to the coding part, this is the simple code which I wrote in order to test the ADC function using Atmega32 chip. Initially, as I said, as you all know, I guess, like I have defined the frequency of a CPU. I have included 3 major library files, which is AVR input output, utility delay, and standard lib header file, which is a header file related to C programming language. And also I have an additional header file which I have included in this code, which is the LCD 16:2 header file, which will be very useful to write the codes related to LCD 16:2 and to display the outputs easily without writing so much codes to initialize and stuff. In this code, I have 2 major ADC functions which I have defined separately out of the main function, which will be like make it easy to reuse, and also it will keep the main code cleaner. So initially the code is ADC init. This code set is used to initialize the ADC as which is useful for our project. So initially I'm making the ADC ports as input ports, as you all know, because we're going to read using those ports, and also ADCSRA 0x877. This will set that as enable of the ADC to 1, and the frequency divider will be used is 120. Since I'm using 8 megahertz, so it is obvious that and also I'm using the frequency divisor 128 to get a value less than 200 kilohertz, which I have explained you earlier. And also I am setting the ADMAX register to 0x400. Using this, I'm using VREF voltage reference of the ADC as AVCC, and also I'm setting the ADC channel to 0. So we are going to connect my ADC device. So basically this is the ADC initialize function which I am using this program, and also you can vary these numbers, vary these values, because these are like hex values of decimals, hex values of binary inputs. So you can, it's obvious that I have explained you how the bits varies and what the variations will occur with the bits. So according to your need, you can set these pins as you prefer, but since I'm using the ADC channel 0 and the frequency divisor was 128 and enable ADC, I use this set of code. And also next thing is the ADC read function, which is used to read the current ADC value which is shown. So since we will be regularly using this, I have made this as a separate function as well, so I can keep on calling it. In this I have two like integer values which I have defined initially, which is AIN low and AIN this is the high values. So initially what I does is the setting the AD register to read mode. So initially we have made it as input. Now using this set of code we start reading it by setting the channel as 0x0f. So once it is read, we have to start the conversions. For that I'm like setting the ADC SC value for 1, so this will start the conversion, and I'm using a while loop until the conversion is done. Once this conversion is done, there will be a small delay, and after that we will get the values which is stored in the ADCL and ADCH as well. So since we are using this method, I want to like multiply the ADCH value into 256 to get the proper value. I'll show the calculation in separate part, and after that I have to add both of these values, and finally this is the value which is needed from our conversions. So I'm using this return function to get the value which we got from ADCL and ADCH. Since this is like more biased towards the lower side, I'm using the 8 bits of the lower side and the 2 bits of the higher side, and it will do the conversion and return a value from this function. So these are the two major functions which is used to do the conversions related to ADC. Now let's move on to the main function. Initially I have declared two variables, like one is char, a character string variable which extends up to 5, and also this used to store the string value which we get by converting this in value which is returned from this function, and also initial value. I have used an integer known as value as well to store some data. Initially this is an LCD command. If you want to know more about LCD, I will give you the link in the description, as well as there will be an eye icon, so you can click and check on the LCDs. So initially what I do is we have initiated ADC, we have initiated LCD, and we have wrote a string which is known as like ADC value, and this is a while one loop. This loop is an infinity loop. It keeps on running. What it does is we are initially initiated the ADC, so it will use this ADC read functions continuously to get the current output from the ADC channel, and we will use this function to display it in the screen. So initially we use this LCD command 0xc4 because we wrote this ADC value, and we have to set the cursor beyond this in order to get a proper reading. And the next value is like the ADC read. This will initiate the ADC function. This will read the initiated ADC function, and it will do the conversion, and it will return this AIN value. It is stored in this integer. Now in order to write this integer into the LCD, we need to convert it to string. For that I'm using the ITOA function, which is a common function in C programming language. So ITOA does is like we are sending value and we need to store that into string, and the value sent is in the base 10 form. This is the simple function which is used to convert an integer into a string without no more further calculations. So it is obvious that we are sending values which is the value returned from the ADC read function, and it will be stored in the string which is a string which I declared initially, and it will be in the base 10 format. So when this is converted to the string, it will write at the position where the cursor is currently existing, and it will print a space and it will return. So this keeps on running. Whenever we change the ADC values, it will respond, this will read it and it will convert it to string and it will be displayed on the screen, so we can get the current output of the ADC channel as well. So let's build this code. Okay, so you can see the build is successful and we have generated the hex file as well. So now we have to go to Proteus and setup and start using or testing this code. So this is the basic setup which we're going to use to check our ADC code whether it's working correctly or not. As you all can see that this is a simple setup where I have like connected a LCD in 8-bit mode, and also I have connected the pot resistor which we will be using to vary the input which we're going to give through this ADC channel. So basically what we're going to do in this setup is like we're going to vary this pot resistance in this pot resistor, and we're going to see whether this microcontroller responds to these changes and whether it displays the correct value. Pot resistor is basically a potentiometer where you can change the resistance by changing this key up and down. So you can see it indicates the percentage at which the pointer is pointing currently. Other than that, I have just connected a 100 farad capacitor, and I have like powered the AVCC as well, since I'm using the ADC channel. So let's check. So here you can see it depicts a value of 410 for 60% of pot resistor value. So let me increase. So you can see when it is 0%, you will get a value of 1023. So it means when the resistor is 0, the supplied voltage is solely passed through this, so it will give the topmost value. And let me bring it down to like 78%. So you can see that the value has decreased up to 125. And let me keep it the resistor in 100. So it is 0 since the resistance is 100%, no voltage passed through this. The value corresponding to this is 0. So this gives the basic idea. While varying this voltage supplied through this pot resistor, this ADC can convert it to a digital value, and the value is converted to a string, and it is displayed here. By using the similar techniques, you can use some other devices such as IR resistors, rain sensor, gas sensors, and like many other ADC sensors which will get analog output inputs, and you can process it through this ADC converter which is embedded to Atmega32 chip. So this is the basic idea on how ADC works in Atmega32. Using the same techniques and codes, you can use various of ADC components to this. You have like 8 pins available, so using each pins you can get various readings corresponding to the environment or the condition you are testing on. So I hope this video will be very helpful to you all, and I hope you got a clear understanding of what ADC and how it works in Atmega32. So thank you for watching my video. Hope to see you guys in another video soon. Thank you for watching.